Hello, physics students, back again. So this is going to be forces, part 2. All right, so forces, part 2. And what we want to look at is at Newton's laws here. So we're going to look at Newton's first and second law. Newton, very intelligent character. His first law we've already gone over is the law of inertia. And the law of inertia essentially says that if something is in motion and wants to stay in that motion, so if I'm moving at 1 meter per second, I want to stay going 1 meter per second. If I'm at rest, I want to stay at rest. Now this is pretty ingenious because if you think about it, in our world, if we've got a ball, right, and we push that ball, it slows down and stops. So that would essentially, with one little experiment, disprove his law, right? Well, he realized that the reason why that ball stops is because there is other things there, like the ground, exerting a force on that ball, causing it to want to stop. And so this is really an amazing discovery because here on Earth, you don't really actually ever observe the first law of motion really in effect. I mean, if you're going in a car and you go around a turn, right? So this is you in a car. Hi. And so you go around the turn, you'll notice that when you go around the turn, you feel your body pushing up against the side of the car. Why is that? Well, your body wants to keep going in that direction. Your body wants to keep going, so it's going to push up against, or you're going to feel pressure up against the side of the car as you turn real sharp right there. You can feel your body going that way. So that would, kind of show here on Earth the law of inertia. You want to keep going in that direction. But otherwise, it isn't really readily observed. And so this was really an amazing discovery because we don't really observe it here, but he hypothesized that in deep space where there's no forces, if you were to shove something and it was to go 2 meters per second, it would just continue in that direction, until another force acted on it. Or if something was at rest, it would never move until another force acted on it. And so then that led him to his second law, which said, okay, then to get things to move, because of the law of inertia, you have to have forces acting on them, right? The ball slows down because a force slows it down. The ball moves in the first place because some force had to push it. So what he said is that if you have a net force, so a net force would be some kind of force that goes in one direction more than the other. If you have a net force, it is going to cause an acceleration. And the net force is going to equal the mass times the acceleration. So this is Newton's second law. It's essentially this little formula right here. And so let's look at that. So force right here, force is measured in a measurement called, of course, a Newton. All right? And what does a Newton equal? Well, a Newton equals a kilogram, equals 1 kilogram of mass times an acceleration of 1 meter per second squared. So that is actually, this is the unit for a Newton. So a Newton would be the force required to push 1 kilogram with an acceleration of 1 meter per second squared. So that's how we define a Newton in force. But that Newton equals mass times acceleration. So let's say that we had 1 kilogram object falling, right, in gravity or through the air, and let's say that there's no air resistance. So what's that going to equal? Well, that's going to equal 1 kilogram times 9.8 meters per second squared, right? So that's going to equal 9.8 newtons. All right, so just kind of a simple way to look at it. Let's say that you knew that. Let's say you had a box, right? And that box right here had a net force. And net force is a really important thing to consider. Let's say that I had a force of 100 newtons on this side. And let's say that I also had, pushing back on it, 100 newtons going the other direction. Well, then there's no net force, which means there's no acceleration. So you have to have a net force in order to cause something to accelerate. Well, let's say that my box is 50 kilograms, right? And let's say that I give a 100 Newton force on that box, and let's say that it's on a freshly oiled ice patch. So that means there's no friction. All right, so what is the acceleration? What kind of acceleration is that? Well, it's pretty easy to solve, as you can see. So if the force is 100, right, there's my net force. If the mass is 50 kilograms, right, then I'm just going to go ahead and divide this side by 50 kilograms. So 100 newtons divided by 50 kilograms equals an acceleration. So I could say this. My acceleration equals 2 newtons per kilogram. Now, wait a minute. I thought that acceleration equaled meters per second squared. Well, newtons per kilogram is meters per second squared. And you say what? All right, well, let me show you how that works. So what is a newton? We defined a newton up here as a kilogram per meters per second squared. So I could rewrite this as 2 equals 1 kilogram, or 2, the unit. So I've got 1 kilogram times 1 meter, right, per second squared, and I'm still divided by kilogram, all right? So I've got kilogram divided by kilogram, and that's going to cancel that out, right? Or I could just, if you wanted to, we could just bring this up here and multiply it like that. And so you can see how this would cancel out right there. So the kilogram cancels out. What are we left with? Voila, 1 meter, or 2 meters, sorry, per second squared. So, so that hopefully goes to show you how the units prove that, that acceleration and mass and a newton are all linked. All right, so in the next video, what we're going to do is we're going to solve a few problems based off of this whole idea.